So now let's talk about LC columns and the kinds of columns that we might use for separations using LC, HPLC, UHPLC, all of those. Okay. Now, columns in general are a little expensive. They can be a few $100s on average. Some are going to be a little bit more, some are going to be less depending on their qualities and the specificity of the manufacturing. But in general, if you're spending under $1,000 on a column, it's a pretty good deal. Now these columns can be very easily degraded by irreversible adsorption. So as we talk about how the analyte is interacting with the stationary phase, if there's some kind of irreversible adsorption where a contaminant has adsorbed to the stationary phase, that site on the stationary phase is no longer available to interact with the analyte. And so that's the kind of degradation that we're talking about. So we tend to use ways to protect our column. So before the column is in the instrument or right around the place that it's added, we might add a guard column. And this guard column is short. It's usually made of the same stationary phase, same proportions as the rain column, what we'd call our analytical column. So it's the same stationary phase as our analytical column. And what this does is that because it has the same stationary phase, anything that would clog up our analytical column is going to be stuck to the guard column before it even gets to the analytical. So you would go kind of analytes coming in, they're going to go through the guard first and then to the analytical column. Okay, and where the analytical column might be up to 30 centimeters in length, your guard column is going to be certainly less than 5 centimeters. Usually it's a 2 or 3 centimeter stretch of column. Now the guard column is going to be a whole lot cheaper than the analytical column, and so this can be easily replaced if it starts to get clogged. Much easier and much cheaper than replacing an analytical column every time it gets clogged. The other thing that we might do is also place some kind of a filter. We would call this like an inline filter. And so there's some kind of filter to get some of the larger debris out even before you hit the guard column. And this is especially important for very messy matrices that have a lot more than just your analyte in them. All right, so now let's turn our attention to the stationary phase. What's going on here with the stationary phase? So our stationary phase is consisted of a support. So remember, we're usually talking about packed columns in LC columns. So we have those small particles, and we're not usually doing open tubular. So I'm going to focus the discussion here on packed columns. And so we have our kind of packing. I'm just going to draw it as a round. They're typically roundish. They can be a little bit irregular shaped. But so we typically have some kind of a silica support. So this is highly pure silica. It's going to have very uniform composition. This can be either regular silica, or it can be something like an ethylene bridged silica. And the difference in these is really a pH. So if you're going to work at a pH that is acidic, so pH of 8, or pH less than 8, you want to use the regular silica. If you're working in a basic solution, you want the ethylene bridge silica that can withstand a pH of 8 to 12. And the reason for this is because on this on the surface of this support, we're going to actually bond our stationary phase. Okay, so this means that we're covalently linking our stationary phase to the surface. Now, this is typically a fairly spherical particle, but we want to get the most surface area possible. And while spheres are great for surface area, there are ways that we can get additional surface area here. So we can actually make this kind of porous. So I'm just going to draw little circles here. Let's say this is a porous surface. So we actually have additional surface area where it kind of dips in. If you think about like a golf ball, well, there's little dips in the surface of the sphere. It's not that it's hollowed out in the center, it's not completely porous, but there is a porosity to the surface that allows additional kind of area for our stationary phase to be held and additional area for analytes to then interact with the stationary phase. So we get the advantage of packing this really tight with these spherical balls, and then we also get an advantage of having additional surface area. Now these are, again, pretty small, right? So we're looking at your size of particles. We said, you know, are with a diameter of 2 to 5 microns for HPLC, or just under 2 microns for UHPLC. And when the pores, then the pore size is even smaller. So you really want your pore diameter to be about 2% of your particle diameter, 0.2% of dp. Okay, which means we're operating on a pretty small size. That's about 3 orders of magnitude left. You're on the kind of nanometer scale now. And for small molecules, they might you might want it to be about 6 to 12 nanometers. If you're dealing with larger molecules like peptides or proteins, you would probably want larger pore diameters, because otherwise your analyte's not going to get into the pore if the analyte is too big. So that's always a consideration as well. So there's a lot that goes into selection of an appropriate column, and it really depends on your analyte of interest as well. Okay, so we have these silica supports. We've bonded a stationary phase to it. Now, what kind of stationary phases might we bond to it? Okay, so we're basically going to take the silica, which is kind of in a lattice structure with silicon dioxide, and in order to do this, we'll take our silicon dioxide and we're going to functionalize it using a silicon chloride with some kind of an R group. And this R group is going to be our, going to dictate our stationary phase. Okay, so in this reaction then you get your kind of silica support that's now bonded to our stationary phase, that R group. Okay, so what kind of R groups can we put on our stationary phase? Okay, well, there's a whole slew of options, and I've just kind of written these out ahead of time so you don't have to just sit here and watch me write. But what I want to point out is there's a whole bunch of different polar options here. Okay, there's things like different amides or amines. Okay, amides, amines. You've got a cyano group. You've got a diol, and then this one down here is commonly called a ZIC helic column. So if you hear of a helic column, it's an abbreviation for a whole lot of words that I'm not entirely sure what they all are, but the helic column has these kind of 2 charged groups, an amine group and a sulfate group, both charged. So we can have some polar options. We can also have nonpolar options. Many of these are just N-alkanes, so you might have like a C18 or a C8 or a C4 here. You may also have it being like a phenyl ring, or you've got a pentafluorophenyl. Okay, those are some options for also having nonpolar. And cyano groups are also pretty nonpolar. They can serve as being polar or nonpolar. They're kind of in the middle ground between the two polarities. Okay, so in general, the cyanopropyl group here that's listed in both columns is really weakly polar or weakly nonpolar. It's kind of in the middle of the polarity scale. So we have options here, and we can define what kind of separations we're doing based on our options for our stationary phase. Okay, so if we have a polar stationary phase, we're aiming to separate out polar analytes, right? They're going to have a stronger interaction with the stationary phase. So we need to have the opposite polarity as our mobile phase. So we're going to use with a nonpolar or less polar mobile phase. Because the whole point is that we want some things to stick here, but we need them to eventually come off. So this is nonpolar or really less polar. The more similar your mobile phase and your stationary phase are in polarity, the faster they're going to come off. So if you want to kind of start with something that's really nonpolar and work your way up to kind of changing it to being less polar, you're going to get kind of the ones that get really stuck and attracted here off towards the end by making your mobile phase look more like your stationary phase. So that's on the polar side, and we actually call a polar stationary phase and a nonpolar mobile phase normal phase. So this would be considered a normal phase separation. Why does this one get to be normal phase? This was the way it was first done. The first stationary phases were polar, and so the first published liquid chromatography studies were done using polar stationary phase, nonpolar mobile phase, and so this took on the name of being the normal phase. Now we can do the kind of reverse where we have those nonpolar stationary phases. We can use these then with a polar mobile phase, or really a less nonpolar. Okay, and when we do it this way, then our nonpolar analytes are going to stick to the column. Our polar ones are going to be more attracted to the mobile phase, and so we get a different kind of order of elution. We call this the reverse phase because it's the reverse of normal, aptly named. But in reverse phase, this is actually the more common one. And the reason for this is that our polar mobile phases, we can use things that are water-based, or we can use things like ethanol, methanol, and a variety of alcohols that are, and ketones that are all very easily obtained. They're cheap to use, and they're easy to often purify and reuse again. Whereas your nonpolar mobile phases are not compatible with water-soluble samples or samples that are in a water matrix, and they're going to be less easy to recycle and reuse. So you're creating a lot of waste when you're doing normal phase chromatography. So once reverse phase chromatography was actually introduced, most of the separations now done are using reverse phase. So even though it's more commonly used, it's not called normal because it wasn't done first. Okay, so that's how that works. Now, between the two different kinds of phases here, there's some different ways in which the interaction between your mobile phase and your stationary phase is going on. Okay, in reversed phase, you have what we call partition chromatography. And this is very similar to what we talked about with GC, where you have an analyte that's dissolved in the mobile phase or bonded phase that's on the silica surface. And so what we have is it kind of dissolves into our our stationary phase. Okay, so here's our stationary phase, here's our mobile phase, and you have your analytes that again are kind of at equilibrium, moving back and forth between being in the stationary phase and in the mobile phase. And anytime during the mobile phase they can move down and then interact with the stationary phase again, and there's some kind of equilibrium there. Okay, so this is again our bonded stationary phase and our liquid mobile phase. So this is just like we talked about with the interaction in gas chromatography. It's the exact same mechanism. Now in a normal phase separation, we do what's called adsorption chromatography. And in adsorption chromatography, it works a little bit differently. We're actually getting solvent molecules competing with the analytes in solution. So here, instead of having this kind of be a liquid sense, it bonded to the surface, in the with a polar stationary phase, they're kind of more discrete locations. So you have kind of your silica backbone here. And we have these kind of polar groups here that I'm just going to mark as P's. So rather than acting as like a bonded liquid, these act as more discrete sites. And so our solvent has counter attracted molecules. So anytime you have a polar molecule, it has a dipole, right? And so you have these mini magnets that can attract other molecules from the solvents. These would be our solvent. And what happens is you have an analyte coming in, and the analyte is going to displace the solvent. And then now the analyte is stuck to the, or attracted to the polar group on the stationary phase. Now remember, this is adsorption with a D, not a B. We're adsorbing, just kind of sticking onto the surface in a reversible manner. So we can have something else from the solvent come through and displace the analyte. And that's how the analyte's going to go back to the mobile phase and move its way down. Okay. Now, the more polar the solvent, the more likely it is to then displace your analyte that's stuck onto your stationary phase, and the faster elution we get coming out of the column. All right, so that's a brief introduction to columns and the modes of elution. There's one other aspect that I want to talk about briefly, and I said something about changing your mobile phase. Now, when you start a separation, you pick a composition of the mobile phase, and this can be a pure substance, it can be a mixed homogeneous solution of two substances. So for instance, you could use pure methanol, or you could use a mix of methanol and water. You can use buffered solutions. You can use a variety of things as mobile phases. But one thing that you can have to consider is, do you want to do what we call an isocratic elution? And that's where the composition of the mobile phase is not changing. Okay, so from start to finish during the separation, the composition of the mobile phase will never change. This is kind of like the idea of an isothermal separation in GC, where the temperature never changed during the course of the analysis. However, we can, much like with temperature programming, where that helped get late eluting ions or late eluting analytes off the column more quickly, like I said, we can change our mobile phase to make it more like our stationary phase in polarity and elute things quicker. We call this using gradient elution. Okay, so this isn't a concentration program. I've seen that answer before on an exam. That's not what we call it here. We call it a gradient elution. And in gradient elution, we're going to change the mobile phase composition to make the polarity more similar to the stationary phase. Okay. So again, when we're doing normal phase and we have a polar stationary phase, we're going to want to make our mobile phase more polar. If we're doing reverse phase and we have a non-polar stationary phase, then in a gradient elution we want to make our mobile phase less polar. Okay, so that's the idea here. And so the next thing you're going to explore in your group work is some elution order and predicting elution order. Yeah, I think that's all I have for these columns and elution principles.